Hey, my name is Queena Williams, and today I'll be introducing to you my Enzyme Lab experiment. So, what we're starting with is with an enzyme. The enzyme is called trypsin, and trypsin is able to have an optimal range at a pH of 8 at 37 degrees Celsius, which is also inside a human small intestine. And so, what we're doing is we're testing trypsin's activity within the pH. So, our question is, how does pH affect the enzyme activity of trypsin? And so we hypothesize that the higher the pH, the more activity that we'll be seeing from trypsin. So going from pH of 8, 9, 10, and 11, it will show more activity as compared to the pH of 6 and 5. And so our rationale is that trypsin functions properly at the body at the pH of 8. 8 is basic, so we predicted the greatest amount of enzyme activity would occur more at a basic pH, which is 8 through 11. And so we made a protocol based off of what we thought would be the best way to go forth with this experiment. So what we did is we started with 15 milliliters of the different pHs ranges from 5 to 11. And so we added a reaction buffer, which is azocasin. And azocasin is able to cleave the trypsin and leave over sulfamidyide to see how much activity occurred within the different pHs. And so we incubated it at 37 degrees Celsius for 20 minutes because 37 degrees is the most optimal temperature for trypsin to have the most activity and the most range of activity. And so at 500 milliliters of microliters of 10% TCA was added to the solution. So TCA is what stops the enzyme reaction so that we're able to see how much went on within the different pHs. So after that, we placed it in a centrifuge at a speed of 12,000 revolutions per minute for 2 minutes. So placing it in the centrifuge will separate the supernatant, which is the liquid, from the pellets. So the liquid is what we're going to use to check out the absorbances to see how much activity occurred within the different pHs. And so the supernatant is transferred into a clean cuvette, which was an instrument used to place inside the spectrophotometer, which is used to check the absorbance and how much of activity occurred within the different pHs. And so it was checked at 440 nanometers using a cuvette from distilled water. And so the absorbance was read at 440 nanometers to see how much activity actually went on. So these are our methods and materials. So our experimental variable was pH because we're checking to see if there's a difference between the different pHs. So our control variable was 37 degrees Celsius because at 37 degrees, that's the most optimal range for trypsin to activate. And the negative control was the substance that did not contain trypsin. So negative control's purpose was to see if any activity would actually occur or not. So it's basically there to be used as an example to see if we're actually getting results from our experiment. And so our replicates, we replicated it 3 times to see variability, to check for outliers, and to also see if our measurements will be constant within the different pHs. So this was our results. You may not be able to see it, but this shows the different pH ranges at the x-axis and the absorbance at the y-axis. And it's also labeled by the legend so you can tell which one is the absorbance. And the little tick lines right here also shows the outliers, which also accounts for variability. So this was based off of the standard deviation and other factors that was calculated to get a more accurate graph to see what our results were. And so this partially supported our hypothesis because we thought that as the pH went up and became more basic, the trypsin activity would be much greater. But after it peaked at the pH 9, it began to decline, and it showed less activity at the pH of 11, which partially supported our hypothesis because it did show some more activity, but it ended up declining at pH of 9. So compared to the other group's results, the first time they did it, they didn't have any replicates, so it wasn't as accurate. So the results were more sporadic. It was more spread out, and you could not tell what type of activity was happening. So compared to the first groups and our results, we're able to see what more happened, and we're able to compare that different activities and the different pHs. And so with our results, we also counted the averages based off of the standard deviation, which is the experimental averages, which ranges from point 2 to point 06. And so we did this for the experimental control groups based off of the different replicates that we have. For averages going for the pH of 5 at 0.026, at 0.6 for pH of 6, 0.7, 0.115 for 7, 0.137 for 8, 0.14 for 9, 10, 0.114, 11, and 0.06. And we also did the same for our controls, but for pH of 10 and 11, they both showed zeros, and our controls actually showed more negative averages. And so what we did is we compared the standard deviations between the negative controls and the experimental controls, see at the variability that went on between it. So compared to the negative controls, so for 5, it showed 0.09 for 6, 0.004 for 7, 0.0001, for 8, 0.0003, for 9, 0.003, for 10, 0.2545, and for 11, 0.001. So this was based off of the statistic of 0.05, which we can either show if we reject a null hypothesis or we fail to reject a null hypothesis. So we did a t-test based off of the p-values to see if we're able to reject or accept the null hypothesis. So this was based off of the pH of 9, since it showed the highest amount of activity. So we compared it with the different pHs, and so for most of them we were able to reject the null hypothesis, except for the pH of 8 because it was the most similar to it. So this is based off of a scale of 0.05. So anything below 0.05, you're able to reject the null hypothesis, but anything above 0.05, you're failed to reject the null hypothesis. So for pH of 5 compared to the pH of 9 is 0.042. For pH of 6, 0.004. For pH of 7, 0.008. For pH of 8, 0.279, which means that you failed to reject the null hypothesis and there was not as much a significant difference. But for pH of 10 and 11, 0.0013 and 0.003. So these values, 5, 6, 7, 10, and 11, we were able to reject the null hypothesis because it did show a significant difference, which was able to support our results. And so for our results and observations, we basically had to start the whole entire experiment because we had forgotten a few elements, but it did go well and we were able to see a difference of color showing the different activities that was going on with the trypsin. So our experimental design was definitely adequate because the results was able to show a definite amount of variability, and we were able to see if there was an amount of change between the pH. So it was adequate. We were able to see a good amount of results from our experiment. So anything that we would do different is nothing, because compared to our first one, adding more replicates showed more variability and better results. And so for our conclusion, our conclusion is that our hypothesis was partially supported because of the peak to the pH of 9 and the decline from the pH of 10. So enzymes are needed because they speed up chemical reactions by lowering the activation energy. And the reason why this is important in living organisms is so that we're able to take part in chemical reactions and so that it wouldn't take that long. For example, metabolism. Metabolism is the amount of chemical reactions that happen in the human body. And so without an enzyme, we wouldn't be able to go through those chemical reactions, meaning that we wouldn't be able to live at an optimal rate.